afternoon to everyone. So in previous classes we seen that there are two types of diffraction, product diffraction and Fraunhofer diffraction. Today in detail we have seen Fraunhofer diffraction as a single slit. This is the setup of a diffraction. So Advaita talked about Fraunhofer diffraction. So what is Fraunhofer diffraction? Okay. If the source of light and the screen are at an infinite distance from the obstacles of slit, then the diffraction is called the Fraunhofer diffraction. The Fraunhofer diffraction experiment was done by Joseph von Fraunhofer. So, listen everyone. Look at the distant light or sunlight and halfly close your eyes. So, do you see a light stretching around into the vertical line? Your eyelashes and eyelids are creating a single slit, and this is an example for Fraunhofer diffraction. So, in Fraunhofer diffraction, the instant wavefront is plane. A plane wavefront instant on the slit AB. The width of the slit is D, and here we are using a convex lens to converge. So, according to Huygens principle, every point on a wavefront is a source of secondary wavefront. When a plane wavefront is incident on the slit AB, each point on the wavefront is a source of secondary waves. The secondary waves, which are moving along the direction of the incident wave, will focus at the point P, where the maximum intensity or central bright band produces P. In this class, we are going to find out phase difference, path difference, phase difference, resultant amplitude, resultant intensity, condition for minima, condition for central maxima, condition for secondary wave, width of central maxima. So first we move into path difference. Path difference of secondary wavelength is reaching point Q from AB. This is AB. To determine that we want to draw a normal. Normal N. The path difference of the wavelength starting from A and B is Bn. So, path difference delta is equal to Bn. To find out Bn, we can consider a triangle APN, and here is theta. Sin theta is equal to opposite angle by hypotenuse. So sin theta is equal to opposite angle, opposite side BN by AB. So BN is equal to AB sin theta. So AB is the width of the slit, which is B. So equal to AB sin theta. Delta is equal to D sin theta. This is the equation for path difference. Next is phase difference. In previous semester, we studied the relationship between phase difference and path difference. That is, phase difference is 2 pi by lambda into path difference. Phase difference is denoted by is equal to 2 pi by lambda into path difference. Path difference is, we found that path difference is T sin theta. Previously we found that path difference is equal to D sin theta. So substituting that 2 pi by lambda into D sin theta. So in between A and B, in between the slit A and B, there are so many variants. Let the slit AB is divided into 8 equal parts. So phi is equal to, phase difference is equal to 1 by n 2 pi by lambda into D sin theta. This is the equation for phase difference. So the equation for path difference is D sin theta. Phase difference is 1 by n 2 pi by lambda into D sin theta. Next is resultant amplitude. In resultant amplitude, find out resultant amplitude. Here equation, plan equation 1, where A is amplitude and phi is phase difference. So substitute phi is equal to 1 by 2 pi by lambda into d sin theta in this equation. So R is equal to A phi n by 2 1 by n 2 pi by lambda into d sin theta. And cancel, 2 cancel, all divided by sin 1 by 2 1 by n 2 pi by lambda d sin theta. Here also 2 cancel. To simplify this, substitute pi d sin theta by lambda equal to alpha. Pi d sin theta by alpha, lambda is equal to alpha. So R is equal to A sin alpha by sin alpha by n. N is very large and n by n is very small. So therefore sin n by sin alpha by n is equal to alpha by n. So R is equal to A sin alpha by, yes, sin alpha by n, we are substituting alpha by n, which is equal to, taking n upward, R is equal to NA sin alpha by alpha, where NA is harmonic vibration into amplitude of each wave. So we are taking NA equal to 80. So R is equal to A sin alpha by alpha. This is the equation for resultant amplitude. Yes, resultant intensity. If we know the resultant amplitude, we can easily find the resultant intensity, because intensity is square of amplitude. Resultant intensity is square of resultant amplitude. So I is equal to, we find the resultant amplitude. So square I is equal to R square. Therefore I is equal to A square sin square alpha by alpha square. This is the equation for resultant intensity. So now we can draw a graph of square by alpha square versus alpha. So at the center we are getting the central right band at a maximum intensity, and either side of the central band maximum and minimum. On decreasing intensity, here the intensity is decreasing. At all the maximum on the either side of central right band are called secondary maximum. Here, either side of the central maxima, the maxima and minima are called secondary maxima and minima. So here the intensity is the first second. This is the first secondary maxima and this is the second secondary maxima. So the intensity of first secondary maxima is 1/20 seconds of intensity of central maxima, and second secondary maxima is 1/61 of intensity of central maxima. So here the second intensity is I is equal to x square sin square lambda by lambda square. The graphical representation is this. Clear? So here the intensity is decreasing so rapidly. Here I in first secondary maxima 1/20 second of central intensity of central maxima, and second secondary maxima 1/61 of intensity of central maxima, and so on. So next is condition for minima. Equation is just we know the amplitude, just square a square sin square lambda by lambda square. A square sin square lambda by lambda square. So I think these four equations are simple. Face d sin theta. Only study part effects d sin theta. Face effects 1/2 by lambda into face d sin theta, and then amplitude a sin alpha by alpha. Intensity the square of amplitude a square sin square alpha by alpha square. Next is condition for minima. Condition for minimum intensity. So I is equal to a square sin square lambda by lambda square must be equal to 0. It is equal to 0 if sin alpha is equal to 0. If sin alpha is equal to 0, the possible values of alpha is equal to 0, pi, 2 pi, 3 pi, etc. But here we can't take lambda is equal to 0, because when lambda is equal to 0, which produce maximum intensity and produce central right band. We want condition for minimum. Therefore, we can't take lambda is equal to 0. Lambda is equal to pi, 2 pi, and 3 pi. So we can generalize that lambda is equal to plus or minus n by pi. Here minimum and maximum either side, so therefore we take plus or minus. And now we can substitute. In previous I said about substituting alpha is equal to pi d sin theta by lambda. Here also we substituting lambda is equal to pi d sin theta equal to plus or minus m pi, and cutting the pi, d sin theta equal to plus or minus m alpha. This is the condition for the minimum for Fraunhofer diffraction, or the condition for minimum intensity. Otherwise, we can say that this is the condition for dark band, formation of dark band. Condition for minimum. So this is the condition. Then we will write here. And next is condition for central maxima. So here also in condition for central maximum, I is equal to a square sin square alpha by alpha square. So we want central maxima, that is at the point P. So I is equal to a square sin square alpha by alpha square must be maximum. For getting maximum, we want minimum denominator will be less. So denominator lambda alpha is equal to 0. For getting maximum intensity for central maximum, so alpha is equal to, substitute the value of alpha, pi d sin theta by lambda, which is equal to 0. This is the condition for central maxima. So when the angle of diffraction is equal to 0, waves travel along the direction of instant wave, produce the central maxima at the point P. This is the condition for producing central maxima at the point P. So and we can write it as I is equal to a square, limit alpha tends to 0, sin square alpha by alpha, sin square alpha by alpha. Or we can write it as I is equal to a square, repeat. We can denote a square as I naught. So I is equal to I naught. This is the condition. And next is condition 4. Is it clear? Condition 4, secondary maximum. So here we are using the concept of di by d alpha is equal to 0. Because of the maximum point derivative, the intensity with respect to alpha is equal to 0. Substitute I is equal to a square sin square alpha by alpha square. So substituting d is equal to d by d alpha into a square sin square alpha by alpha square, which is equal to 0. So a square we can take outside. And apply the quotient rule. So quotient rule is denominator into derivative of numerator minus numerator into derivative of denominator. 2 sin alpha cos alpha minus sin square alpha 2 alpha all divided by denominator square. Here denominator is alpha square, so alpha square alpha raised to 4. So as we want to find the possibility of this becomes 0, but we want this becomes 0. So here S1 can't be 0, lambda square can't be 0. Only cos alpha minus sin alpha is equal to 0. So only possibility of making this equal to 0 make alpha cos alpha minus sin alpha is equal to 0. So alpha is equal to sin alpha by cos alpha, which is equal to tan alpha. So to find the points and solve the equation, we want to solve this by graphically. Here we are taking y is equal to alpha and y is equal to tan alpha. So the graphical representation is this is the graphical representation of tan alpha and here the graph of alpha. So the point intersecting the graph is 0, 3 pi by lambda, 5 pi by lambda, 7 pi by lambda, etc. The intersection points of alpha and tan alpha. So here lambda is not equal to 0, therefore we can't take 0. So the points of intersection are 3 lambda by 2, 5 lambda by 2 and 0, 3 pi by 2, 5 pi by 2, 7 pi by 2, etc. So can we generalize? Lambda is equal to 2 pi plus 1, 2m plus 1 into 5. Alpha is equal to 2m plus 1 into 5 is the condition for secondary maximum, and we can substitute alpha is equal to pi b sin theta by lambda equal to 2m plus 1 into 5. Cut the pi on both sides. So 3 sin theta equal to 2m plus 1 into lambda. This is the condition for secondary maximum. And the last one, width of the central maximum or area width of the central maximum. theta by lambda is equal to 0. Sorry, m phi plus or minus m lambda. Applying the condition for minimum at the point that is equal to m is equal to 1. D sin theta by lambda is equal to lambda. So sin theta equal to sin theta here no lambda. D sin theta equal to m lambda, and d sin theta is equal to, we are taking m is equal to 1, d sin theta is equal to lambda. Sin theta is equal to pi by lambda, pi by d. There is a figure. This is the y distance between maxima, two maximas, and we are taking this as f because this is focal length and theta. So we know theta is equal to arc by radius. Radius, which is equal to arc is y and radius is s. Here the theta is known as half angular weight. When we can say the full angular weight, it is like that. We can say this angular full angular weight. Here half angular weight. So the angle of diffraction theta is very small here. So sin theta is equal, we can approximate sin theta is equal to theta. Theta equal to theta is equal to y by lambda. Previously I write that theta is equal to y by d, and here it is y by s. So linear width of the sorry, y is equal to lambda f by d. This is y. We want 2y. 2y is the width of the central maxima. So 2y is equal to 2 lambda f by d. Or 2y is equal to 2f lambda by d. This is the equation for width of central maxima. So width of the central bright light for the red light will be more than that of the violet. That's it.